So pyramid decompositions are useful because they provide information at multiple scales that is not apparent in the original image. Most people have probably heard about the Gaussian and Laplacian pyramids, but today we're going to learn about the Steerable Pyramid, which is a more powerful decomposition that has applications in texture synthesis, early vision tasks, and optical flow. So what we're looking at here is actually the spatial domain decomposition of a test image, which is this right here. And in this video, we're going to mainly go over the application and implementation of a steerable pyramid, but we're not necessarily going to go into the theory. I do have an article that's linked in the bio that actually talks in more detail about the theory. So a steerable pyramid is a multi-scale, multi-orientation linear decomposition that provides localized information at different scales and orientation. It is an over-complete transformation, means that it contains more than enough information to reconstruct the original image. So let's go ahead and get started. So the first thing we're going to do is we're going to get a test image. So I actually have a script here called test image, and I also have an article that goes over this in some more detail. But basically, here's what we do. We define a size of our test image, which is n. I'm choosing 512. We take a mesh grid of the x and y indexes and reshape the column vectors, and then we get the radius right here. So what the radius is, it's just going to be the L2 norm of the x and y index. So we basically take the square, then take the square root to get the radius at every location from the center, and then we convert to float 32 and then squeeze that extra dimension out. So we just get a nice singular value r, and then we add it to our function right here. So func right here is going to be our test image function. I have a couple of examples right here, and I'll actually display all of them. So this right here is our very basic function. So right here we have a DC center, and if you're not familiar with what a DC is in terms of image, it stands for direct current. And what this means in terms of images is it's just flat. There's no change, there's no frequency variation. So we call it DC. It comes from electrical engineering, and you might hear about it in image processing. So let's actually go ahead and plot this F0. So right here we have the DC center, and I'm just going to see what that is. It's 255 on the edges, and we could actually plot a diagonal of this. So plot the diag, put a semicolon to suppress the output. You can see right here we have DC is 255, and then we have some sinusoid right here, and then we go back, snap back to the DC in the center, sinusoid out, and then DC on the edges. So that's this diagonal cross section right here. So in this next one right here, we have something a little bit more advanced. We have the same DC center right here and the same DC edges, but instead of the sinusoid, regular sinusoid, we have a chirp. And a chirp, what a chirp is, it starts at one frequency and it goes higher or lower. So let's plot that to understand what that actually is. So we have F1. Okay, so here's what our image looks like. We had this earlier, and we have the DC center, we have this thick ring right here, and the rings slowly get thinner and thinner as we go out in frequency. So when we take the 1D cut, let's start, let's just start from the center right here. So we start at the DC center, and then we go into the sinusoid. So we snap down to the start, since we're using to the bottom because we're using a cosine, and we actually go up, down, and we start to see that the wavelength gets shorter and shorter as we go up in frequency. So this is a chirp up, and we could also chirp down. So we can actually see what a down chirp looks like. This isn't with the actual image, but when we come in from the outside and go into the center right here, we start at a high frequency and go to a low frequency. So actually I'm going to see what changing this to a sine looks like. Let's restart this. I don't really like it. I'm changing that back to a cosine. I don't like that at all. So I'm going to change it back to a cosine and restart it. So this is what the test image looks like. I have another article that explains this, and just for fun, I have this crazy test image right here, which gives us all kinds of stuff. So we have, basically, we start DC, we go high frequencies, and then we go still slower to the lower frequencies as we go to the output. So it actually looks better if I don't do the diagonal, so it looks clustered. Let's just take a cut right here. So you can see it's so the frequencies are so high, they're kind of meshed together in the plot, but I think you get the idea. So we're gonna go F1 here and get our, and right here is our chirp out to the edges. So the first thing we do is we get our steerable pyramid class. I have code for the steerable pyramid here. I have some pyramid-based utils here that are going to help us with our steerable pyramid class. And we notice that we have three hyperparameters. This one right here is for complex. This is for another time where we are going to do complex steerable pyramids, but right now we're going to do regular steerable pyramids. So we have depth. Now this is the height of the pyramid. So this is going to determine the amount of radial filters that we have. Orientations is going to be the amount of angles that we steer to. And if this doesn't make sense, we'll see it in a second. So I'm just going to scroll down here. So right here we have the different filters. Right here we have the first level of our decomposition filters, and they're steered. This is steered at 0. This is a 45. This is a 90. And what's this? 45 plus 90 is 135 degrees. And you can see that we don't necessarily need to steer all the way because we take a lobe on each end. And so let's actually go to what the decomposition looks like. So here is basically the first result when you Google steerable pyramid. It is this link right here. So this has been around for a while. So what you do here is you take a high pass and a low pass of the image. So I have that here. I have the high pass filter and the low pass filter, and the low pass filter is actually cropped. But actually I can change the code to not crop it. What did I do here? Let's look at the code. Did not plan on doing the full reconstruct image DFT full. Pyramids, filters. What am I doing here? Oh, it's a build pyramid full. Okay. What am I doing here? Images, filters. Oh. Okay. I forgot to set crop defaults. Hopefully that worked. Okay. Let me get to this in just a second. Okay, so now we have the high pass filter and the low pass filter. We see that the high pass filter accepts all the higher frequencies and rejects all the lower frequencies, and the low pass filter only accepts the lower frequencies. And then in between this circle right here and this inner circle right here, we have our radial filters. And you can see, let's actually go to another plot. I will show you all this in a little bit, but basically we have these three radial filters right here. Once we sum up all the orientations, this is basically what we get. We get a ring here, and the ring slowly gets smaller and smaller. So that's what we have here. So once we get this low pass filter, we recursively take these little band rings out and cut them at different orientations. And that is what's going on here. We have our first ring right here, and we're saying, oh, let's get 4 little cuts right here and get different orientations. And when we go to our actual spatial domain decomposition, here's what we get. You can see that we don't have that much frequency information at these bands. And then we go to the next one. So the next one is this right here. We go a little bit lower in frequency and cut them at multiple orientations. And the number of orientations is a hyperparameter that we can set. And once again, we have these different cuts in spatial domain, these different cuts, and these different cuts. And that's what corresponds to these filters right here. So we could go through the code for this. And the first thing we want to do is obtain the filters right here. So we have something called the radial values. And this depends on... Actually, let's go to the bottom. This bottom has some good examples. So I have a tutorial that has a lot of these things in it, and I actually experiment with many things. So the depth is the number of spatial scales, and orientations is the number of steering angles, hence the steerable filter. It could be called an oriented filter, if you ask me. And the T-width is the width of the transition region between the high and low pass filters. So these radial values, they control the distance between each filter, or each radial filter. So we have this right here. If we change the depth to say 14, we're going to have a lot more radial values. And you can see we're going to have a lot more filters. And I'm going to go back to 4 to make things easy. So the first thing we want to do is we want to get a polar grid. We want to convert the Cartesian coordinates into a polar grid in frequency space. So we're going to just display it real quick to see what it looks like. We kind of wrap around here. I think we start at, I think it goes from pi to negative pi to pi. So that's about negative pi to pi, and then the radius. You can see that we're very small in the middle, big on the outside. That's what we'd expect. I think radius is going to be 0 to square root of 2. Yep, I'm pretty sure that's square root of 2. Okay, sorry, I didn't really plan to go through all this, but I think it's going to help drive the point of what we're seeing. So what we could do is we could actually obtain the low and high pass filters for each radial value, and that's what's in this code right here. We're going to have this function called getRadialMask, which basically obtains the current low and high pass filters. Each time we call this function, we're going to actually have a different rval in, and every time we put this rval in right here, we're going to shift this log radius by an octave. So we shift the log radius, and I can kind of just show you what it looks like right here. So let's just PLT plot. That is, we will shift it by the first one. That's not what my M show. So we shift it by the first one, shift it by the second one, shift it by the third one. That one. So that's actually kind of hard to see. So let's just take this and let's just plot the cut. Maybe that will give us a better representation. So we have the first one. So you can see we're moving this up a little bit. Then we clip based on the T-width, that gives us the high mask. So here's how the high mask changes as we go through this right here. And the T width right here, the transition width, controls the region of transition between the high pass right here to the reject right here. So I think this is a little bit of a better representation. We can see as we scale back one octave, we're going to come in and make this high pass filter more and more acceptive to these lower and lower frequencies till we finally get to our final frequency right here where we have quote unquote everything but the DC. So I have some more plots of this down here. We can see the first one, high pass filter with an R-val of 1, and the second one with R-val of 0.5. And as we go down the line, as you just saw, we're going to get thinner and thinner DC reject and thinner DC or low frequency accept. And we could also see the impact of the T width. So let's set T width to 0.01 just for an extreme effect. You're going to see this transition. That's not helpful. Hard-coded at the one there. All right, let's do this again. Right here. This is the abrupt transition. So it seems to behave a little bit better, and you can see right here there's a sharp cutoff. It seems to behave a little bit better when we have it around 0.5 to 1. I'd just leave it at 1. That's what the original implementation in MATLAB did. So now we can see how we take the radial masks. So the essential way to do this is we basically take the previous low pass mask and multiply it with the current high pass mask as we quote unquote recursively do this. And in fact, we actually use a loop instead of recursion to obtain these filters. So we get our initial masks right here, and then we continuously iterate and get radial masks, and then we get an angular mask for each orientation. So let's go ahead and see what this radial mask looks like if we take our previous low pass filter and our current high pass filter, multiply them together, we get this ring of high values right here, and we can keep doing that and get smaller and smaller rings as we go along. So I don't like what this is doing to this. Okay, so we get that right there. And now let's see what the angular masks look like. So this formula is not actually in the original paper. You have to research and go to some of the other papers that cite it, but it is in the official MATLAB implementation, and I've been able to convert it to Python code. And right here, we take the angle mask, and then we can see what happens at each orientation. And we basically get this for each one, and we're going to end up scaling or multiplying these rings with these orientation masks to get our final filter mask. So this is the frequency domain decomposition filter for the first level, and we keep doing this, and as we saw earlier, we keep doing this for all the other levels until we get to the smallest frequency, and then we finally get to the low pass filter. So let's go back to here. So we could see the responses. Let's do build pyramid full. Alright, hopefully this works. Okay, so here's the frequency domain responses. And you can see in the DFT right here that we are getting some information. It just doesn't translate to something very visible in the spatial domain. But here is the decomposition at level 0, 1, 2, 3 at orientation, 0. What just happened? Outputs are collapsed. Not meant to do that. There we go. Okay. And orientation 0, 1, 2, 3. And the pyramid right here, I have just a giant picture right here so we can actually see. This is the high pass right here. And here's the low pass. You can see we get a lot of nice DC information. All the contrast is going to come from here. And we can see our first orientation. It's, almost invisible to see right here, but if we blow it up, we see we do get some nice high frequency information. It's just very hard to see. If we take the absolute value, we can actually get a better representation of it, and you can see we actually are getting information. So the giant cut of frequency space is actually giving us useful information. So now let's go investigate the reconstruction. So actually, we did talk about building the pyramid. So building the pyramid is quite simple. So we're going to take the image and our filters, and in this case I have crops right here. They're cropped for visualization. So we're going to build the pyramid in the frequency domain. So the first thing to do is take the discrete Fourier transform, or DFT, of the image, and then we iterate through the filters. And in Python, this isn't the efficient version. The vectorized version uses NumPy, but we're going to go through the iterative version because it's a little bit easier to think about. We're going to take the cropped image DFT and multiply it by our filter. Since we're doing convolution in the spatial domain, multiplication is the same as convolution in the frequency domain. So that's what we're doing right here. We're multiplying our filter with our DFT and frequency domain, and then we actually take the inverse Fourier transform, the real part of the inverse Fourier transform, and add that to our pyramid list. So this is what we're going to do for our pyramid building. And we could also get the Fourier domain pyramid by just appending the DFT to our pyramid. So, and for the complex pyramid, we don't take the real part, we leave the real and imaginary, but like I said earlier, that's for another video, probably a much shorter video since we're doing the majority of the work here. So the reconstruction part, I can walk through that. So the reconstruct image, so what we're going to do, the first thing you do is you reconstruct the DFT. So you get a complex 128 matrix of the original height and width to store the DFT. And what we're going to do is we're going to actually accumulate the reconstructed pyramid decomposition. So the first thing we do is we get our pyramid, our spatial domain pyramid, our frequency domain filters, and our crops. And the first thing we're going to do is we're going to take the DFT, unless we've already passed in the DFT, which is what this frequency argument does. So we're going to take the DFT of the pyramid and frequency shift it, and then we're going to once again scale the filter, which is can also be considered a basis, by our DFT in the frequency domain, and then we're going to accumulate this in the reconstructed DFT. We're accumulating these reconstructed subbands, and once we get that, we simply take the real part of the inverse DFT and we get the original image. So that's what we're doing right here. So you can see that we can actually reconstruct the original frequency domain with a pretty good degree of accuracy. We take our reconstruction and we actually get a pretty good, but let's check the numerical differences. And you can see that we are very far under 0 right here with the sum of absolute values, and then the root mean squared is very, very low to the -28th, practically 0. And you can see that, if we take a diagonal cross section, we get a pretty good reconstruction. So that's all for this one. I hope you learned a little bit about steerable pyramids. And then next video, we're going to learn about complex pyramids. And then we're going to dive into some applications for this topic. So I'll see y'all later.